All right, so let's find the moment of inertia. Let's find the moment of inertia of a solid sphere rotating about a central axis. So I have a solid sphere here rotating about some central axis. So let's just go ahead and set up a coordinate system here. So X, Y, and Z. And what I'm going to do is I'm going to break it up into a series of disks. So I have some disk here at some height Z here. And I know that the moment of inertia is the integral of m dm times r squared. Let's write that a little bit better. dm times r squared, or some people prefer putting the dm at the end, so integral of r squared dm. And we can actually do slightly better. We can do it this way. We can do it slightly better because I know that the moment of inertia of this disk here is equal to, since it's the mass is infinitesimally thin, it's going to be 1/2 dm r squared. We derived that in a previous video, that the moment of inertia of a disk, so the moment of inertia of a disk is equal to 1/2 m r squared. So this is radius of disk here. That's what we did in a previous video. So since the mass is infinitesimally small, the moment of inertia is infinitesimally small. So I would be equal to 1/2, the integral of 1/2 radius of the disk squared dm. Now, dm is this small little sliver right here. So I know that the mass is equal to the density times the volume, or the differential of the mass is equal to density times the differential of the volume. The volume of this particular disk is going to be, well, we have the area times the height here. So the area is pi times radius of the disk squared times the height, which is some differential with z. And so this becomes the integral, I'll bring the 1/2 out, r, the radius of the disk, so this is rd right here, radius of the disk squared times rho pi radius of the disk squared dz, which is, well, let's bring the other constants out. So I got 1/2 rho pi times the integral of rd to the 4th dz. Well, if I look at this triangle right here, I have a triangle. This is z this way, this is rd that way, and this is the radius of the sphere here. That's the radius of the sphere. And so I know that rd squared is equal to big R squared minus z squared. So this becomes 1/2 rho pi times rd to the 4th. So this is r squared minus z squared to the 4th power. Squared dz, because rd to the 4th would be rd squared squared. So this becomes 1/2 rho pi times integral r squared, try that again, r to the 4th minus 2r squared z squared plus z to the 4th dz, which is 1/2 rho pi integral. That is a constant. So this becomes r to the 4th. Oh, we actually have limits of integration. So it's going to go from negative r to r. This is z is negative r. That's z is equal to r right there. So negative rz from negative r to r minus 2/3 r squared z cubed from negative r to r plus 1/5 z to the 5th negative r to r, which is 1/2 rho pi times, you stick r in and then negative r, so we end up with r to the 4th times 2r minus 2/3 r squared times, again, that's another odd function, so this is going to be 2r cubed plus another odd function, so we have 1/5 times 2r to the 5th. And we'll bring this up to here, so we end up with 1/2 rho pi times, so we have 2r to the 5th minus, we have 4/3 r to the 5th plus 2/5 r to the 5th. I can bring r to the 5th out, so I get 1/2. Let's just use another sheet of paper here. So my moment of inertia so far is 1/2 rho pi times 2r to the 5th minus 4/3 r to the 5th plus 2/5 r to the 5th. Factor r to the 5th out, so I have 1/2 rho pi r to the 5th, 2 minus 4/3 plus 2/5, which is, get a common denominator of 15, so that's rho pi r to the 5th, 30/15 minus 20/15 plus 6/15. So that's 10, so it's 16/15. 1/2 rho pi r to the 5th times 16/15, which is 8/15 rho pi r to the 5th. I know that rho is the total mass over the volume, which is 4/3 pi r cubed. And so I can plug that in here. So I end up with 8/15 times big M over 4/3 pi r cubed times pi r to the 5th. Now we get to do some canceling. Pi cancels out. 3 of the r's cancel out. And now I have 8/15 divided by 4/3, which is 8/15 times 3/4. That goes in 5 times, that goes in 2. And so what I'm left with here is 2/5 mr squared. And that is the moment of inertia formula for a solid sphere.